All right, so up until now, we have not talked about powers of matrices, and that's just because we hadn't yet defined multiplication. But now that we have talked about multiplication and we know what multiplication means, we can, in some situations, define what it means to calculate the power of a matrix. And really, in particular, that when I said in some circumstances, really our only limitations is that the matrix A be square. So, well, how do you define powers? Well, for starters, we need to talk about what the exponent is. So I'm just going to introduce a letter k. So I'm going to say for an integer, that just means a whole number. So an integer k, which is, let's say, first we'll start with an integer k that's greater than or equal to 1. So if that's the case, if we have an integer k that's greater than or equal to 1, we can just define what it means to take a and raise it to the power of k. Well, what does it mean? Well, it's just use the same sort of definition that you would use in the case of real numbers. It means just take the matrix A and multiply it by itself, but just do it k times. So you're going to have something like this. A times A times A, and so on. And you just keep on going, and you'll do that k times. Which that might actually be quite computationally intensive if k is large, or if the matrix A is large. Like if A is a 2 by 2 matrix, that's one thing, but what if A was a 10 by 10 matrix? That's going to make calculating products a lot more difficult, and hence it's going to make calculating powers much more computationally intensive. So this is something that is not immediate. It's not something you can just write down really quickly. It actually takes some computational time to actually evaluate powers of a matrix. But well, that's if k is greater than or equal to 1. What about an exponent of 0? What do we define a to the power of 0 to be? Well, that's our notion that we have written down above, multiply it by itself k times. Well, what does that mean to do it 0 times? How do you multiply something by itself 0 times? That doesn't really lift so well to that circumstance. But ask yourself, what do we do in the case of real numbers? How do I raise a real number to the power of 0? Well, we just say it's equal to 1. And what matrix behaves very much like the number 1 in the sense of multiplication, and that is the identity matrix. So that is what we do. We see it's taken to be the identity matrix. Now, it's taken to be the same, to have the same dimensions as A. So if A were a 4 by 4 matrix, then A would be A to the 0 would be the 4 by 4 identity matrix. Maybe let's actually add a comment here. I didn't even think about this till right now. Let's maybe just remove any chance of confusion. Let's say, assume that the matrix A is an n by n matrix. Then this is automatically going to be the n by n identity matrix. But it is common not to write that. Usually you won't bother writing it because it's automatic. So yeah, that's the definition of powers of a matrix. Now, if A is not a square matrix, you can't do this. And why is that? Why is that the case? Let's first write this down. And while I'm writing this note down, think about why that's the case. Why is it that we need to assume that A is a square matrix? So I'm going to say if A is not square, this doesn't work. Why is that the case? Well, let's think about it in terms of an example. Let's write down a non-square matrix. So let's say, how about I'll let C be equal to, how about 1, 2 for the first column, 3, 0, and then 5, 1. Well, how would I compute C squared for this matrix? Well, think about it. What would the dimension diagram look like? Well, if C squared, if I tried to use this idea up here, I would just take C times C. But what about the dimension diagram? If I go C and I try to multiply it by C, I've got, well, 2 by 3 and a 2 by 3. The dimension diagram fails to be satisfied, right? These two inner numbers do not match up. So for that reason, C squared is undefined. And that generalizes to any matrix that is not square. You cannot calculate powers of non-square matrices. It just doesn't make sense.